big. Well, it's too big. All right, so we will, oh man, it's way too loud. All right, so like again, we're trying to understand a little bit better the problem of solving Laplace's equation on some domain where we have specified the value for the solution on the boundary. That's the thing we did today that I didn't really, I just kind of did it. And the thing that I think is stopping people right now is partly just that we don't have enough experience with what the level curves of complex differentiable functions look like, right? I mean, I've given you guys more problems, maybe you've seen some notes, but I mean, and I will admit, even for, I mean, I've thought about this stuff a long time. You know, you ask me what are the level curves of the exponentials component functions, I don't know, right? I actually have to, I really have to stop and think about that one. But the logarithm is a nice function. The level curves of the logarithm are pretty nice because the logarithm. So can you erase this monstrosity? Yeah. Have you been hanging out with Sam? You're both in the chess club. Interesting. So if we look at log z, right, which by definition was the natural log of modulus z plus I times arc z. In this case, you know, this is my u, this is my v. If we look at u equal to a constant, right? Natural log of modulus equal to a constant. Exponentiate both sides. We've got that the modulus of z is equal to e to the constant. So the level curves of the real part of the logarithm are circles, which is interesting because lots of applied problems concern solving things on circles. So this is an important observation. If we want to find a solution to Laplace's equation that involves a circular boundary, maybe the log of the absolute value of a complex is a good thing to work with. On the other hand, if we look at v equal to a constant, well, that's the argument of z, right? But what that means then is that, you know, well, that's a level curve is what? It's a ray. It's a ray from the origin, because that says that there's a constant angle. I mean, that is already geometric. The argument is constant. That is angle theta. Theta equals c. If I use the notation argument is theta instead of argument, it would be like just in our face.
What do you mean it's a ray? What a ray is? I don't understand. Why you can make this?
Well, so the level curve is the set of all z. I mean, u of x plus iy equal to that, right? V of x plus iy equal to that. We're saying find all x plus iy in the complex plane that solve the equation c equal to theta.
Okay.
That's a ray. Yeah.
Are you normally looking at u and v or just at u? Or like, does it matter or what's the difference?
I mean, it doesn't matter. If you can find a real part or an imaginary part of a complex function that serves your purpose, it doesn't really matter what the other side of it is. It's just as long as I'm thinking about, well, I'm just looking at both for the sake of, you know.
Sorry. Thought you
You're fine.
It's hours.
Oh, but you're welcome to have a seat.
I just wanted to,
Oh, you should get, if you want.
just review that, what I had done on
Oh, perfect, thanks.
it.
I'll take that, no problem.
Okay, thank you very much. Sorry to interrupt.
No, I don't mind.
So like almost on the board over there, you could have chosen B and done something with that instead. It just
Well,
would have
yeah.
a different, like a different region that you're looking at.
Right, so my point is that the logarithm is a natural thing to work on. If we have circles as boundaries, the logarithm is nice. If we're talking about a sector, the argument function is nice. But they're both solutions to Laplace's equation because they appear as the real and imaginary components of a holomorphic function with the principal logarithm. Now, but the fine print is, of course, that the principal logarithm is not holomorphic if you go all the way around. So the argument function will have to, we've got to be careful not to, like argument would not be good if I tried to do it. Here's the problem I would not want to use plain old argument for. You know, if I want to make this 10 and make this minus 10, like that, and here we're looking at, you know, what is this? I don't know. 5 pi over 6, right? And this over here is minus 5 pi over 6, yeah? Then I can't be using the principal argument there because that's where the principal argument has a jump. No big deal. I just got to use some other argument. So like if I was trying to solve the Laplace equation up in here with these boundary conditions, I would try something like phi of z equals to a arg naught of z plus b, where because arg naught is defined on the I think I called it c plus, right? I mean it's got to jump at the positive real axis. That's where it ceases to be continuous. It jumps from 0 to pi there. The principal argument, you know, just arg, it's got to jump at pi minus pi. So we have to avoid that. It's a discontinuity and consequently
So you can have a region that overlaps the discontinuity.
right. I mean, if I have the discontinuity in the function, that means it's not complex differential there. So our stuff breaks down.
So you look at the region that you want to work with and then try to find something that fits it.
That's the first order. That's the first thing to do. But the second order logic here is you think, wait a minute, this is a more complicated region, but I know about Mobius transformations and I know how to take this more complicated region and map it to a simple region that I already have a solution for. That's the next step in the adventure. But I think first we should spend a little bit more time on this part at the moment. Does that, so like, do you understand what I'm saying? I mean,
This right here, yes.
so then, you know, what's the principal argument of, so if I let me, you know, pick a point anywhere in here, we call this C1, we call this C2. So if I pick phi of z for z in C1, I get a times, what's the principal argument of anything here? I assume the arg naught of anything here, it's just 5 pi over 6, yeah? That's 10, right? And then on the other side of it, I would have phi of z for z in C2, yeah? What's the principal argument there? A times what? What's the, it's not minus 5 pi over 6, right? Arg naught takes values from 0 included to 2 pi. So this is actually it.
7 pi over 6.
What's that? 11, no, yeah, 7 pi over 6. So because pi is here, and then you go pi over 6 more. So it's 7 pi over 6. Okay, but you got it. I mean, anyway, you guys understand. So there you go, that's equal to minus 10. Now let's not even do it, okay? 2 equations, 2 unknowns, you can solve it. You can find the A and the B. When you do that, bam, that's a solution to Laplace's equation on that sector, which produces 10 on the upper and minus 10 on the lower.
You may just need to let it digest.
Let it digest.
Yeah.
I guess I will suffer the mic.
There's been class already, so the algebra is not.
I hear you. I'm not feeling very snappy myself either. I mean, I might be a little bit snappy in the figurative sense, but in the mathematical sense, not so much. All right, for the sake of people not being deafened, I mean, make the mic level go back to a reasonable amount. If I leave the mic level at 75 after I plug it in, it would not be good. There we go. All right. So for those of you who just came in, all we're doing is, his question basically was, could you do more of what you did in class and just try to make more sense? That's what I'm attempting. So what's on the board right now is, well, that's not helpful. So like over here, the point of this one, for the guys who just came in, if you, I don't know if you care or not, but Stacy, could you, yeah. So over here we were talking about if I wanted to solve Laplace's equation over here, and I hope x squared minus y squared actually is this curve, is it? If I put y equals to 0, do I get a solution? Oh, I do. Yay! Actually, so this region D takes the hyperbola as its boundary, and if I put a 10 here like that, when we restrict to the boundary, we get 10, and we've solved Laplace's equation in this region. Now, accidentally, where else did I solve it? I've also solved it, like over here. And I mean, to be honest, I can't help but solve it everywhere because this function is entire. I mean, this function this is a harmonic function on the whole plane, you know. But my focus was just in here for the starting. So I'm gonna post the homework for next Friday, hopefully later tonight. It'd probably be helpful for you guys to see me actually do one Mobius transformation, like how to find it, right? Let me do that. Actually, those of you who just came in, did you have any questions about problem 29? I think I already talked to you about it earlier, so you're okay, right, Emily? So and I need to post the PDF of the, like you asked me for, James. I do mean to post that. I haven't gotten to it yet. Oh man, I left my complex notes in my office. I got to stop pinning stuff to my inbox. It's out of control. Got too many. Whoa. Huh. I think the scanner broke my scan into 2 pieces. That's good. It's getting smarter. All right, here's the really cool idea. We do z minus z1 times z2 minus z3. Z minus z1 times z2 minus z3. divided by z minus z3 times z2 minus z1. Z minus z3 times z2 minus z1. This is a particular trick, if you will. This is a Mobius transformation. It's kind of a standard Mobius transformation, all right? Like a what do you want to say, canonical one or something. And so let's figure out what this does. What does it do? We plug in Z1, we plug in Z2, we plug in Z3. Something special happens. Let's see what happens. What happens when we plug in Z1? You've got, and oh, by the way, these are distinct points. So if we plug in those distinct points, what do we get? We get, so can you can see it, right? Up 0 up here, non-zero down there, so we map to 0. What happens when we plug in 2? We get 1. 2 minus. Oh, yeah. So we get 1. Excellent. What happens when we plug in Z3? Yeah, we get something over 0, which we understand to be infinity. I mean, we're going to extend the value for the Mobius transformation to the extended complex plane. So that, yes, that would be naturally understood to be infinity. So this Mobius transformation, what it does is it takes the points Z1, Z2, and Z3, all right, wherever they are, and it maps them onto the, if you want, the real line at 0, 1, and then way out here, infinity. So it's just, that's what T does. And when I have more time to talk about it Monday, hopefully I will in part explain that Mobius transformation takes circles to lines or circles. This time, if my Z1, Z2, and Z3 are genuinely as drawn, what this map would do is it would take, let me draw them slightly differently so it's easier for me. For my graphical convenience, if Z1 and Z2 and Z3 look like that, well, there's some circle that they lie on, right? 3 points uniquely fix a circle unless they're collinear, in which case they fix a line. As question? Okay. And so this circle gets mapped to that. So you can think about a circle in the z-plane getting mapped to the half plane in the w-plane. And the other neat thing is it preserves orientation in the sense that if I have 1, 2, 3, what's on the left? Oh, outside. If I go 1, 2, 3 like that, this is the left. So this is actually not a circle. This is actually it's everything but outside the circle is the region. And then 0, 1, infinity. So if I walk along that, the left is up here. So this Mobius transformation actually maps the exterior to that disk, the outer annulus, to the upper half plane. And it does it bijectively. That is true. Inside the circle is mapped bijectively to the lower half plane. And the edge of the circle itself is mapped to the real axis. Oh, yeah, of course. Thank you. Have a good weekend. You guys aren't going to waste your time on like football or anything, are you? Yeah. Good answer.
Every point on that circle
family over football, yes.
Every point on the circle will be mapped to the real number.
Yes. So, thanks, Emily. So if I want to come up with a mapping which maps, the words. Let's be more specific. Suppose you want to map the suppose I want to map the unit circle, yeah, to this over here. Actually, maybe be lazier. I want to map it to this over here. And I want to do, let's see here. I suppose I want to map, I'll fix -1, yeah? And I will map, I want to map I to 0, and I want to map 1 to infinity. Is that, let me make sure I'm going in the right order here, just a second. Let me think of it the other way around. I want to send 1 to 1. Sorry. I want to send I to 0. I want to send -1 to infinity. All right. Let me send 1 to 1. Send I to 0. All right. Then what should my? Because then, what will that be? Which kind of? I guess that's the lower half plane, isn't it?
Everything inside.
I don't want that. I want the upper half plane. How can I make it the upper half plane? How should I do that?
I would switch.
Just send 1 to infinity, right? I send 1 to infinity. I'll get it eventually here, guys. I send 1 to infinity. I send -1. I send -1 to 0. I send I to 1. That would do what? That would make
Yeah, that's right.
that would make the left side the upper half plane. So here's the inside over here. And again, I'm thinking about them. So here's the orientation of the circle that I'm thinking about, yeah. And so this is the orientation of the boundary I'm thinking about. You might say, like, there's a distinction between which one's 1, which one's 2, which one's 3 in this formula. Oh, did I choose the right points to have the standard formula? I did, right? That was actually accidental. But I had to do that given our current state of progress, right? My choices are infinity, 1, 0, which I used, right? Infinity, 0, 1. All right. All right. I think this is going to work. So what would the formula be? Z -1, yeah? And then Z2 minus, I'm sorry, I should actually just write down, right? My Z1 is 1, Z2 is -1, and my Z3 is I in my current thinking. So I have Z -1, and then Z2 minus Z3 is -1 minus I divided by what? Z minus Z3, which is Z minus I. And then z2 minus z1, which is what? Yeah, negative 2.
So one way to look at this is you're taking 3 points on any circle in the plane, and you're saying, and you're picking another 3 points on the circle you want to map to, and plugging it into this equation that will give you the transformation to get that new circle.
Oh, I haven't showed you the most awesome thing yet. This is a gateway to the awesome formula. I haven't shown you the.
But this is generalized because the real line can be seen as a circle going to infinity.
Well, yes, right. The real line is a circle through infinity. This does send a circle to a circle, but I mean, I can literally send a finite circle to a finite circle, any other finite circle, because what I can do is I pick another one, W1, W2, W3, right? And I can send those by the same formula to this, this, and this.
Right.
And then if this is S, if I want to go from this guys to those guys, I simply do T composed with S inverse. So T composed with S inverse is going to map from Z1, Z2, Z3. It does more than this, but it takes this set and it maps it to that set. Yeah? And but that oh, I'm missing a sentence here. Yeah, this is accurate, but there's something beyond this that seals the deal. Let me come back to that because my brain is stuck on that at the moment. Does this work?
It maps the wrong one.
Oh no.
If you plug in Z1, that maps to 0, but we want to map that to negative.
There's just infinity. Yeah. What's that? Oh, did I choose badly?
No, you said you got 0, right?
I thought we wanted to map
Oh.
one to,
Yeah, we want one.
1 to infinity, but that maps
Oh, right. I have to. My labeling is off, isn't it? We're going to have to. We have to think through this, right? Let's think. You can create it though, right? By the principles we just laid out. So what we want to do, like you said, one goes to infinity, right? So that means we're going to put a pole down here with 1, right? And we want minus 1 to map to 0. That means we put a z plus 1 up here, right? Then we want the remaining thing of I. We want I to map where? We want I to map to 1. So that means when we plug in z equals to I, the fraction has to work out to 1, right? Which all that means is you got to put I minus 1 up here, and you got to put I plus 1 down here. And that way, flippity floppity cancely, that works out to, so and then that's, I'm using the principles that were used to create this formula and ignoring the labels.
So what might a question look like that involves Mobius transformation?
Oh, there are many.
What would you say, like,
Find a Mobius transformation which maps a given circle in the complex plane to a different circle in the complex plane. Find a Mobius transformation which maps a given circle in the complex plane to a particular half plane. Those are typical questions. Or, but okay, so this, I think, is the transformation from that unit disk to that upper half plane. And we could actually, maybe we should rationalize, I don't know. The larger point here, though, is we can use the thing I wrote on the board to find actually kind of a very, very, very nasty example here. Because we can solve Laplace's equation can be solved up here. You know, suppose you want a boundary values of, let's just keep it relatively simple. Let's say we want a boundary value of 2 here. We want a boundary value of -2 there. Yeah. Or, you know what, let me be even lazier. Let's suppose we want a boundary value of 0 here and want a boundary value of pi here. Yeah? What's your, if you want boundary value 0 and boundary value pi for the positive and negative real axis, what do you use for your, what's your solution to Laplace's equation that fits those? It's a sector that's our camera person left. I didn't notice. Been talking off the edge of the world. Oh well. So, I mean, let me just say it. How about this? Phi of W equals to just arg W. This is W over here. Over here we've got Z.
So you can find solutions to Laplace's equation on any circle in the complex plane by mapping to that and then finding the solution.
That is true. That is indeed what we're after. What he's saying is, because we can solve Laplace's equation on the half plane, and because we can map the half plane to any circle we want, through the conformal mapping theorem I stated at the start of class today, that means we can solve Laplace's equation on any circle. Now, let's follow it through for this one. So that's a solution to Laplace's equation in the sense that, and let me use the same letters I was using earlier today. I was using this, right? So that satisfies psi UU plus psi VV equals to 0. And it also has that it restricts to 0 on the positive boundary, and it restricts to pi when we go to the negative U axis in the W plane. So then we can use that to write down a corresponding solution to Laplace's equation on the disk. And that corresponding equation, phi, right, of Z, is going to be the argument, well, I'll write it symbolically to start with it. It's going to be psi of T of Z. Because, you know, T of the circle, I can say that, I mean, T of the circle is equal to the U axis. That Mobius transformation maps the circle to the axis. And in fact, it's more than that. But so this, which explicitly is principal argument of Z plus 1 times I minus 1 over Z minus 1 times I plus 1. That is a solution to Laplace's equation on this disk, which satisfies the following boundary conditions. We have to see how the boundary tracked under the Mobius transformation, like which part went to which part. So let's focus here on between 0 and between. Let's see here. Between where did I start? Where is it pi? Between 0 and infinity, right? Where is that coming from? That's coming from 1 right? And where did the minus 1, right? So I believe it's hard to tell you. Is it the upper half or the lower half? I think it's the upper half, all right? So I'm pretty sure that the upper half here will all have phi equal to pi there. It's not defined. The solution will not be defined at the jumps. And then on the lower half of the circle, we're going to have the solution have boundary value 0 on the lower half of the circle if I have not made a stupid mistake in my thinking here, because that's where this part maps to. We can check real quick. Where does 1 map to? What map? So I allegedly maps to 1, right? And so is I up here? See, I did bad. Yeah. So I just, yeah. I tell you, I can't be trusted. I mean, that makes, I mean, I is the, I goes to 1, so that means that wherever I is where the boundary value 0 is attained, yeah? Make sense? I mean, now, to really convince you, what I need to do is I need to take this and I need to find its Cartesian form. That's going to sting a little. See, because this is x plus 1 plus I, y, times I minus 1, divided by x minus 1 plus iy times I plus 1. I got choices. I can multiply those complex factors out in the numerator and denominator and then rationalize, or I can rationalize the 1 plus I upstairs, so I just got a number downstairs. I think I'm going to do that. If I multiply by I minus 1, so the conjugate of this is 1 minus I times 1 over I plus 1, what do we get? We get 1 minus I over 2. And then that puts a 1 minus I squared upstairs, which is what? 1 minus I times 1 minus I is what? 2 minus 2I. 2, listen to me. 1 minus 2I plus I squared, yeah? So in other words, it's minus 2I. So it definitely pays off to, so what I'm saying is I can erase this, right? And just write instead, that actually just simplifies to minus I. See, because, again, 1 over 1 plus I times 1 minus I over 1 minus I is 1 minus I over 2. But then I multiply that by the 1 minus I in the numerator. 1 minus I squared gives me minus 2I. So minus 2I over that 2 gives me just a minus I overall. That was probably better than what I was about to do. And then, but then you got to, you want to make the denominator behave. So you just multiply by x minus 1 minus iy over that. And what's that give me? It gives me x plus 1 times x minus 1. Oh, that stupid I. Son of a gun. All right, fine. Let me multiply this minus I through before I do anything else. This stink. Minus I, and that gives me plus y, yeah? All right, try. So that gives me minus I times x plus 1 times x minus 1 minus iy squared, and then the real terms, plus y times x minus 1 minus y times x plus 1, all divided by x minus 1 squared plus y squared. Yeah, and then I think some stuff happens, right? Like, great. Can you guys see what anything? Looks like we got a plus yx, a minus yx, right? So like, we got a minus y, minus, it looks like we got minus 2y for the real part. And the imaginary part, plus I times what? What's the imaginary part? It looks like I got a, what do I got? Plus I times what? Plus I times, should I put a minus there? It's more natural if I put minuses in there. I'll put minus I times, you said x squared. It's x squared minus, x squared plus y squared, yeah? Minus what? Minus 1, right? Because the divided by x minus 1 quantity squared plus y squared. This is the calculation I needed to do before class today to make the lecture decent. That didn't happen this morning for me, unfortunately. I believe that's the Mobius transformation, and it's like, we can, now let's check ourselves, right? We can easily check if this is like legit or not. If we put in, see, because now if we put in 1, what should happen? It should, yeah, it should blow up. Does that happen? Remember, putting in 1 means we're putting in x equals to 1 and y equals to 0. Because it's the complex number 1, yeah. So that denominator, good news. What happens when we plug in I, we're supposed to get back out 1. Plugging in I means putting x equal to 0 and y equals to 1. X equal to 0 makes that 1. That's 1, so we got a 2 in the denominator. Upstairs, we've got, whoa. Did you get, what'd you get? What are we plugging in again?
X equals 0, y equals 1.
Sorry. X equals to 0, y equals to 1. And my claim was that was z equals to I, right? And you said it worked out to what?
Minus 1, I think, because on the top you get minus 2, and then on the bottom you get 2.
So minus 1. Is that good?
Should be 1, right?
Yeah, it's supposed to be 1.
I think there's probably just a sign there somewhere.
Apparently. So I lost a sign somewhere.
If it's multiplying just by I instead of minus I, then it would work.
Yeah. I'm not sure where that is, but let's put it back in there. I mean, there needs to be a okay, so minus. So apparently I dropped the sign somewhere in this. You gotta be careful. I'm happy we're just off by a sign, though. And how about the other point? I'm kind of scared to check. We're also supposed to send 1 to infinity, right? Wait a minute. Oh, we did that already. We're supposed to send minus 1 to where? Minus 1 is supposed to map to 0, right? So, in other words, x equals to minus 1, y equals to 0, right? What happens with that? Oh yeah, the denominator, listen to me, numerator is 0. so then it's really interesting to think about what's the argument of this expression. Think about this expression and what its argument looks like on the unit circle. On the unit circle, we've got x squared plus y squared equals to 1, which makes this term right here be gone, right? So in other words, this expression is real on the unit circle. And its positive denominator and its numerator is plus 2y. After my sign is corrected, moment of truth. So when y is positive, we have a real number, a positive real number. When y is negative, we have a negative real number when we evaluate this thing on the unit circle. I mean, the input to this thing on the unit circle. So what's the argument of a positive real number? It's pi. It's going to be 0, right? Like I said, 0. And we plug in a negative real number, which corresponds to the lower half of the circle, we get pi. That's a proper example of this technique. That's what it is. We get the phi. This evaluates to pi on the whole lower half circle. And it evaluates to 0 on the upper half circle. And in between, it does other stuff, but it solves Laplace's equation everywhere inside. But here's here's the grown-up version of this question. You've got some. No, I'm just saying you got some domain D, right? And it looks like some kind of crazy nonsense, right? And it's got some boundary which is horrible. And maybe you want it to be like 3 here, and over here, between here and here, you want it to depend on like f of xy equals to xy on this part. I mean, you could talk about non-constant boundary dependence too.
It doesn't always have to be a circle.
No.
It's crazy.
And then the question is, can you take that amoeba-looking garbage and like transform it to something that you can solve Laplace's equation on? Because if you can find such a transformation, you solve Laplace's equation on the nice space and just track back. We're not going to answer that question in its full generality this semester. I don't think anyone has. But the next section that I don't cover, and have not scanned, the Schwarz-Christoffel symbols show how to like map regular polygons into a circle. The Riemann mapping theorem says that any simply connected domain in the complex plane can be bijectively mapped onto the unit disk. It's got more than that. It also has a certain uniqueness if you specify, I think, a point or something. I should write that down Monday, actually. Not prove it, but write it down. The cross ratio is the thing I haven't showed you yet, guys. The cross ratio, because we're stuck with the 0, 1, and infinity, but the formula for the cross ratio so there's notation for this. This thing is here's his notation: Z, Z1, Z2, Z3. This is the so-called cross ratio. And so he points out that, this condition just amounts to saying that the two cross ratios are equal. I will try to explain this again Monday, but that's Yeah, so all you got to do is set these two things equal, solve for W, that's your Mobius transformation. let's try it out. It's too good to be true, right? Well, can I erase this?
You made a video, right?
Yeah, whoa.
Well, it was on the,
Yeah, we're okay. I think we're okay. I just said some stuff over here, but
everything on the center should be good.
all right. I think after this we can go, yeah? I mean, you can go now if you want. Just for what? New notes, just for complex. Well, I have pretty much removed all mention of the evil A calculus after chapter 6. Yes?
I'm assuming that somebody has already decided upon approximation methods for a domain like the one you have up there. If I just have some kind of random domain, is there a way to get a decent enough approximation of what?
Is there an approximate notion of conformal mapping? I don't know. I don't know. I'm not a master at this. I mean, I know that this, like I said, the Schwarz-Christoffel transformations do a lot more than what we're doing, because they concern finding bijective holomorphisms between finite polygonal, I think, regions and something nice. But the devil's in the details to find the formulas for the mapping. The coefficients that define such mappings involve integrals which defy closed form solution. So, yeah. But you can do a lot. Suppose we want to map this circle. So we got what? We got like minus I, we got minus 1, and I don't know. Oh, how about this point over here? What's this point if I want to make it a unit circle? What should that point be? Minus 2 minus I? Okay. Suppose we want to map that circle to, so is Z-plane, yeah? We want to map that circle to, and you guys pick the other circle, I don't know, whatever.
Any circle?
Sure.
Mapped about the origin.
The origin one?
Or too easy.
It's fine, we can do that. Origin? All right. And which 3 points on that circle do you want to think about?
1, 1.
1 and what?
Oh, yeah.
That's 0, 1. 0, 1, 1, 0, and -1, 0.
So you guys want minus 1, I, and 1? And let's, we want to think about the orientation, like we want to order the points, I think, 1, 2, like, you know, so that when I walk around the edge, this is the inside, yeah? And so I want to do the same over here. So what I'm saying is that my Z1 is equal to minus I, my Z2 is equal to minus 1, my Z3 is minus 2 minus I, and I want those to map to W1 equal to 1, W2 equal to I, W3 equal to minus 1. The method is to set the cross ratios W1 I minus 1 equal to Z minus I minus 1 minus 2 minus I. And then we have to, what are those? So like we have to, you know, I have to figure it out. So There's a W, there's a W, there's a Z, there's a Z. That much I know. Past that I gotta think. So minus W1. I'm gonna write it down symbolically first, okay guys? 2 minus 3. That hopefully will keep me honest, although it's debatable. W3, W2 minus W1. And the same pattern, but with Z's. These are actually pretty good questions for a complex test because, I mean, once you guys are at the end of this discussion, you realize, oh, there's just a straightforward procedure to map a circle to a circle or to a circle to a half plane. We just have to pick 3 points and calculate the cross ratio, right? But the nice thing about this problem is to actually sort through it, it tests on your ability to actually do complex algebra. Because it's all about algebra at this point. You know, and I mean, it's not, I'm not sure it's even really complex algebra, it's just algebra. That's here. So that's W minus 1. And what's this? W2 minus, so that's I plus 1. And then we've got W plus 1 times W2 minus W1, which is I minus 1. And that's equal to Z minus, what was Z1? Well, Z plus I, right? And minus 1 plus 2 plus I, yeah? And Z minus Z3, Z3 was, so that's Z plus 2 plus I, yeah? And actually, I'm not sure this makes a great test question. It seems like a drag to grade. Set up the cross ratio that can be solved to give. Maybe that's a better question. Set up, but do not solve for W. Z2 minus Z1. Where was I? Minus 1 plus I. All right. So let's think about some things here.
Will this work for any 3 points on the new circle, or those 3 points have to follow the same?
If you don't follow the same orientation, what you'll do is you'll map the interior of the left circle to the exterior of the right.
Is that a bad thing?
Depends on what you want. It's a bad thing if you're trying to solve Laplace's equation inside the right circle instead of outside. If you're trying to solve Laplace's equation outside the right circle, maybe that's worthwhile. Yeah.
So like the I plus 1 and I minus 1, that all goes away, right? Like cancel out.
Oh, does that? Does it cancel here?
Yeah. There's, on both sides, there's I plus 1 over I minus 1.
Oh, this is the. It's the same.
Yeah.
I can literally erase the extra factors.
Yes.
Oh, that's cool. We should have done this in class so I could just be done with it. Let's see here. So we got Z plus I over Z plus 2I. Thank you, Bethany. That's helping me to get to my car sooner. I appreciate that at this point. And so then you cross multiply and suffer. Well, I mean, it's not too much suffering. So W minus 1, final derivative, W minus 1, Z plus 2 plus I is equal to Z plus I, W plus 1. So we've got a WZ plus W times 2 plus I